semaphore is a technique for managing concurrent processes entering their CS. It chooses the value of a simple variable to keep track of interacting processes. Before we go any further, what is a semaphore? A semaphore is a sign in everyday life which provides a signal. Semaphores, for example, tell a train driver if it is safe to use the track. If another train is on the same piece of track, the semaphore provides a signal to the driver to wait. Semaphores are also used in airports. For example, the flags used by the person guiding the plane to its parking location. In an OS, semaphores are also a signal mechanism. They are quite similar to test and set, and they enforce mutual exclusion. A semaphore signals when a resource is free and can be used by a process. In other words, another process is not in its CS using that resource at the time. This is our first example of a semaphore, and it is a counting semaphore. It is an approach to mutual exclusion. At the start, S is initialized to N, and that would allow N processes to enter their critical sections. In this case, we'll set S equals 2. Therefore, 2 processes can enter their CSs at the same time. So let's work through this. Let's say 3 processes, P1, 2, and 3, are trying to print at the same time. All execute the process code here in blue, and they execute this forever. That is, until their request has printed. So they keep looping through this code again and again and again. These slides roll on automatically, showing you how this works. If you need to stop the content or to go back a step or forward or whatever, use the navigation keys. First, P1 arrives. It starts executing the process code in blue. The first thing it does is call the procedure wait. When it starts executing the wait code, the first thing it does is decrement S. So the value changes from 2 to 1. Now S count is 1. After that, the wait pseudocode checks if S count is less than 0. It is not. It equals 1. Because S count is not less than 0, P1 exits the wait pseudocode and goes back to the process code in blue. And then it goes straight into its CS. Now P3 arrives within a second of P1. Again, it executes the process code. At this point, S count is equal to 1. The process code calls wait, and that decrements the S count. So now S count has changed from 1 to 0. The check here tests if S count is less than 0. It is not. It is 0. Therefore, P3 exits the wait code and returns to the process code. It starts executing its critical section. At this point, P1 and P3 are in their CS. Next, P2 arrives, and it starts to process. As usual, the first thing it does is to call wait. That decrements S count, so it drops from 0 to -1. Next, the wait checks if S count is less than 0, as usual. This time it is less than 0. So as it satisfies that wait check, the P2 continues executing the wait code. The other 2 times it exited. This time it continues executing the wait code, and the process is placed in a queue. P2 is then blocked. In other words, mutual exclusion is applied, and the maximum number of processes are in their CSs. The semaphores are preventing any new processes entering their critical sections. All new processes have to queue. A few more seconds pass and P3 finishes in its critical section. So look at the blue process code again. Once the CS is complete, a process calls the signal pseudocode. The signal begins by incrementing scount. So it was -1. After S3 increments, it is 0. The signal checks if scount is less than or equal to 0, and it is. Then signal code continues, and the next thing that it does is remove a process from the queue and make that process available for execution. So that process is P2. That was queuing. It's now on the ready list. The first thing you'll notice here is that P3 has disappeared. After calling the signal, it continued and did its remainder section, and then it exited. Now, as P2 is repeating the process code forever, the next time it executes, it will get to execute its CS. Once you understand the theory of a counting semaphore, you will understand the theory of a binary semaphore. With the binary semaphore, S can only have values of 1 or 0. In other words, it is like a counting semaphore that only allows a single process into its CS. Once that single process is in its CS, mutual exclusion is enforced. Nothing else can get in. Any other processes must queue.